In the last lecture, we had introduced canonical correlation analysis. Basically, canonical correlation analysis is the way of calculating the correlation between two sets of variables. So, we take linear combinations of these two sets and find the combination which gives us the maximum correlation among all possible linear combinations coming from the two sets. That is what the first canonical coefficient gives us, and subsequently we can choose other canonical correlations as well. What we will do today is to look at the relationship between this canonical variables as such, which are the linear combinations, and the original variables. We will look at how this canonical correlation coefficients are related to the multiple correlation coefficients and the simple correlation coefficient. We will also look at how we can calculate this given us data set, and finally we will look at an illustration of canonical correlation computation. What if we actually standardize the variable? So, instead of looking at the original variables, suppose we standardize them. So, instead of x1 we now have z1. z1 consists of r elements, each of which comes as from the corresponding xi's, it is xi minus mu by sigma. So, we standardize this. Similarly, instead of x2 we have z2. And what would you expect the correlation between x1 and x2 to transform to in terms of z1 and z2? This would remain the same. We know that if you have a base or a scale change, the correlation does not change. So, this happens for the canonical correlations as well. So, if we build up canonical variables from the z1 and z2s rather than the x1 and x2, we will end up with the same canonical correlations, although the canonical variables themselves would be slightly different. How would that be different? Let us have a look at this combination here. You see that if I have, just look at the first variable x1. So, x1 minus mu, if I look at this, the combination was ak prime x1 minus mu 1, which led to uk. Now, we can break this up as element wise, ak1 into x1 minus mu 1 plus ak2 into x2 minus mu 2, etc., up to akr into xr minus mu r. And if we just multiply and divide by the corresponding variances, or rather the standard deviations, we can write this as ak1 root over sigma 1 1, x1 minus mu 1 by root over sigma 1 1, etc., up to akr root over sigma rr xr1 minus mu r1 divided by root over sigma rr. And you can very easily see that we can go from one to the other. In this case, the coefficients would now become ak1 root over sigma 1 1, that is for the z1 variable, ak2 root over sigma 2 2 for the z2 variable, and akr root over sigma rr for zr. So, we have this different coefficients now, and this coefficients, if we start with a and multiply a by a matrix V11 to the power of half, then we can get to this new coefficients. What is V11 to the power half? It is basically a diagonal matrix with the diagonal elements equal to sigma 1 1's root, sigma 2 2 root, etc., up to sigma rr root. So, V11 is sigma 1 1 diagonal, sigma 2 2 in the diagonal, sigma 3 3 in the diagonal, etc. This is basically a diagonal matrix, and if you multiply a by this, we get to the new canonical variables for the standardized. So, in this case, we can actually go from one to the other, just changing the canonical variables, but without having any effect on the canonical correlation itself. We had looked at the canonical variables and the canonical coefficient, and we have found out how to actually derive them. What we did was, we found the first canonical variables as those which maximizes the correlation between the two sets of variables x1 and x2 by taking their linear combinations. But what about the implications of the results? First of all, how do I identify these canonical variables with the original variables? Let us have a look. So remember, I have U. U is basically the set of canonical variables that I have got. Since the first set x1 had R variables and the second set x2 had S variables, U would be of dimension R. So I have U1, U2, UR, Uj corresponding to the jth canonical variable from the first set. And this U can be written as AX1, where A actually consists of the eigenvectors P1, P2, PR. So these are the linear combinations that we actually used. So A would be the matrix comprising of this eigenvectors. Similarly, let us define V as a S-dimensional vector, or in this case, since we are just restricting ourselves to canonical variables, it will also be of R dimension, because we had assumed that S is greater than or equal to R and we can only go up to R of the canonical correlations. So V again we will be defining as S-dimensional vector, of which we will be interested in only the first R, is given by Bx2. So these are the linear combinations that we can get, and the first R of this gives us the corresponding R canonical variables that we have for the set of X. Now let us look at the covariance between U and X1. So U is the canonical variable and X1 is the original variable. Now this is given by covariance AX1 and X1, which is equal to A sigma 1 1. Now because variance of Uy is equal to 1, the correlation between Uy and xk1 is obtained by dividing covariance of Uy xk1 by the square root of the variance of xk1, which is sigma kk to the power of half. And therefore, correlation between Uy xk1 is the same thing as the covariance between Uy and xk1 divided by square root of sigma kk. And introducing this R by R diagonal matrix V11 to the power minus half, which we have used before when standardizing, the kth diagonal element sigma kk to the power minus half, which is the diagonal element of V11 to the power minus half, and which is the one we are using to standardize the xk's. We now can find the correlation between U and x1 as the correlation between U and V11 to the power minus half into x1, which is the covariance between Ax1 and V11 to the power minus half x1, and this is given by A sigma 1 1 into V11 to the power minus half. Similarly, we can calculate the correlations between U and x2, V and x2, B and x1, and the results would be similar. So what does this correlation matrices give us? Let's go back and look at the first one, which is correlation between Ux1 is a R by R matrix, and the elements gives us the correlation between each of these variables, each of the canonical variables with the corresponding X elements. So there are X elements in X1 and there are canonical correlations. Correlation matrix actually gives us the relationship between this group, and it helps us to understand how each of the canonical variables is related to each of the original variables of the same set. One other relationship that we need to look at, as we mentioned at the very onset, that the canonical correlations looks like a general case of the type of correlations that we study in early statistics, like the simple correlations or the multiple correlation. So can we get these correlations as special cases of canonical correlation. To look at that, consider first the canonical correlation between two variables. So we are assuming that the first set has one variable and the second set also has one variable. So R is equal to S is equal to 1. So in that case, the correlation between x1 from the first set and x1 from the second set is basically the linear combinations ax1 and bx1, and which would be the first correlation, first canonical correlation. So it will have square root of lambda 1 as the correlation between x11 and x12. Now suppose we have more elements in the first set, and suppose we just stick to a single element in the second set. In that case, we can write the first set of variables. If we want to pick up a single variable from this, we choose a prime as 0 0 0 1 0 0 0, where 1 comes in the kth position. And in that case, when you look at the correlation between the kth variable of the first set with the jth variable of the second set, which we pick up by taking b equal to 0 0 0 1 0 0 0 with the 1 coming in the jth place, then this would be equal to the correlation between a prime x1 and b prime x2. But the maximum correlation between a prime x1 and b prime x2 is given by the first canonical correlation, which is root over lambda 1. And so this must be less than equal to root over lambda 1. So what does this tell us? This tells us that if we pick up any variable from the first set and compute its correlation with any variable from the second set, then this must be smaller than the first canonical correlation, which really means that if we go back and look at the general variance covariance matrix sigma, remember sigma is sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2, where sigma 1 1 and sigma 2 2 are the variances of x1 and x2 respectively, whereas sigma 1 2 equal to sigma 2 1 prime is the covariance between the two groups. So sigma 1 2 has the correlations between the individuals from the first group with the individuals from the second group, and all these elements would be smaller than square root of lambda 1, because the canonical correlation would be the largest of the correlations that you can have, or it will be larger than even the largest of the correlations that you can have between one member from this first group and one member from the second group. This is what this result tells us. Next, let us look at how the multiple correlations are related to the canonical correlations. Now recall that if I look at one variable from the first set and all the variables from the second set, then this would be given by the maximum correlation between x1 and b prime x2. This is what we call the multiple correlation, and this would be equal to square root of lambda 1. Now if we have more than one variable in the first set, then as before we pick up the ith variable from the first set and we have the correlation between xi1 and b prime x2, and that would also be smaller than square root of lambda 1, because square root of lambda 1 gives us the maximum correlation whatever combination you take. So we can say that the multiple correlations should all be bounded above by the first canonical correlation. So as in the case of the simple correlations, canonical correlations also act, the first canonical correlation in particular acts as a bound for the multiple correlations as well. Now let us look at the problem of calculating canonical correlations given a data set. So suppose we have data on R variables from x1 and S variables from x2, and there are n observations. Remember, in this case it has to be paired observations, paired in the sense that x1 and x2, these sets must be paired, So we have paired observations. So we have what looks like as a n by r plus s dimensional data matrix. And from this data matrix we can calculate x bar, which would be x1 bar of dimension r and x2 bar of dimension s, so that x bar has a dimension of r plus s. We can also calculate the sample covariance matrix as S, which is S11, S12, S21 and S22, where S are the usual variance covariances obtained from the samples. And then we have the linear combinations u hat and v hat as a hat prime x1 and v hat is equal to b hat prime x2. And we find the canonical correlation by finding the correlation between this u hat and v hat. And the results follow as before. So, we will not be discussing it here, only that instead of starting with sigma, we now start with the sample correlation matrix and follow the same technique and get the sample canonical variable combinations and the sample canonical correlations. So, this would be similar to what we do, and hence let us look at an application of this result. In this case, let us look at a data set from Johnson and Wichern, which is basically a part of a larger study on the effects of organizational structure on job satisfaction. And there are two sets of variables. One is consisting of 5 variables, which are feedback, task significance, task variety, task identity and autonomy, and a second of 7 variables, which are supervisor satisfaction, career future satisfaction, financial satisfaction, workload satisfaction, company identification, kind of work satisfaction and general satisfaction. And there is a feeling that these two groups might be related. And what we do is that we pull up this 12 variables, 5 from the first set and 7 from the second set, into a single matrix. And these are poses questions to 784 executives. From this 784 executives on these 12 variables, our matrix comes out as follows. We can see this, and if you look at the 2 blocks of the diagonal, you can see that they gives us the correlations between each of the variables from the first group with each of the variables of the second group. There are 35 of these observations, and the largest one of them is 0.38. It's not very easy to comprehend as to how these two groups are related, and therefore we will try a principal component analysis on this. And once we do that, we can get the linear combinations for the first canonical variable as u1 hat is equal to 0.42 x1 plus 0.21 x2 plus 0.17 x3 minus 0.02 x4 plus 0.44 x5, that is for the first group, and v1 hat as 0.42 x6, 0.22 x7 minus 0.03 x8 plus 0.01 x9 plus 0.29 x10 plus 0.52 x11 and minus 0.12 x12. So, the first 5 are from the first set and the last 7 are from the second set. And the sample canonical correlation comes out to be 0.55. So, we can say that one group has a reasonably good influence on the other, or they are reasonably related to each other. So, this is how we can of course calculate the other canonical covariates, but generally these are not of so great importance as the first canonical covariates. We can also find out individual relationships between the EYs and the XIs, etc., but the main focus would be on the first canonical covariate. Now, to wind up, what does this help us to do. If we see that two sets of variables are very highly correlated, the first thing that we need to look at is, this is a summary result. Okay? So, the way you do your multiple correlation, you can do your canonical correlation as well. Multiple correlation, you are looking at one variable and another set of variables. In the canonical correlation, it is more of a generalized case in the sense that now you are looking at one set of variables with another set of variables. This is the first advantage. We put the correlation between these two sets into one single number, the first canonical covariate, instead of into RS numbers. The second advantage is that if this correlation turns out to be large, then probably we can say that these two sets of variables are very closely related to each other, and hence we can discard one set and work with the other only. So, that will also help us in some ways to choose a smaller set of variables to work with by discarding the larger set, and since they are highly correlated, the results come out to be similar. So, it can also be used as a dimension reduction technique. So, these are several ways that we can use canonical correlation methods in analyzing a given data set. In today's lecture, we have looked at the relationship between canonical variables and the original variables, and this gives us a very good idea as to how these original variables relate to the given canonical variables. We have also looked at how the canonical variables and the canonical correlation coefficient relate to the multiple correlation coefficient, and finally to the simple correlation coefficient. We see that the first canonical correlation coefficient acts as an upper bound both to the multiple correlation coefficients as well as the simple correlation coefficients. We also looked at a data set which helped us to illustrate how we can find canonical correlations and how we can interpret these results. So, canonical correlations can be looked upon as a way of summarizing the relationship between two data sets.